Now let's see how to build a service or an algorithm on top of the DKA system. Let's look at broadcast. So this is actually a research work that was published, Efficient Broadcast in Structured Peer-to-Peer Systems by Sama El Ansari and so on in the International Workshop on Peer-to-Peer Systems. So we want to do broadcast. Why do we want to do broadcast? Well, we want to do dissemination, for example, to send information, or arbitrary queries. For example, all the items are stored in all the nodes. We want to do a query for all the items. So we basically can broadcast the query to all the items. So we need an efficient broadcast. So the problem is, given an overlay network constructed by a peer-to-peer DHT system, find an efficient algorithm for broadcasting messages. The algorithm should not depend on global knowledge of membership and should be of equal cost for any member in the system. So how do we do broadcast? So the idea is that we use the structure of the DHT to construct a spanning tree. And we derive this from the decision tree of the distributed KA search. Notice that every node of the distributed DKA search is actually the root of a tree. So if we take a part of this tree, we will get a spanning tree. So technically, in our terminology from the first part of the course, this is equivalent to a best effort broadcast because it relies on the correctness of the initial node. So here is a case of distributed K search with k is equal to 2 in this example. So we start with an interval with a level 1, level 2, level 3, and each level we divide the interval into 2. So we have this tree. But notice that the number of nodes in the system is not going to be equal to the number of nodes in this tree. Usually there's going to be many, many less nodes. We have a sparse system. Okay. So how can we do broadcast based on this tree? Well, we can try naive solutions. Let's say we do flooding. We use this tree and we just flood it. Well, the positive, the pro of this is that we will have a high guarantee. We will reach all the nodes, but we will have a lot of redundant messages. Nodes that are because of the sparsity, nodes will receive many messages redundantly. Another way, a simple way, is using the predecessor-successor pointer just to traverse the ring. Well, that's sequential. There's going to be no redundant messages there, so that's better than the flooding. All the messages will be useful, but of course it's very slow because of the sequential, and it's going to be sensitive to failure. So can we get the best of both worlds? Can we get high guarantees and no redundant messages? So that's where we can do it. So basically, the idea is the following. We have this tree, and we send the broadcast along all of the children at each level. But each of these children has a limit, a forwarding limit. It will only look at a slice of the tree below it, and we make sure that these slices are not overlapping. So basically, disjoint intervals. So that means each node will receive a message exactly once. So the way it works, so here's the idea. So here's an idea with a k is equal to 4. So assuming that we're doing a broadcast starting at node 1, now we will basically send a message, send the broadcast to each child. Note that we don't have to send to itself. So we don't, at the left one, we don't have to send it here. But we send to 3, we send to 6, and we send to 9. 3, 6, and 9. But the node that the message that we send to 3 will have a limit of 6. Since we're already sending a message to 6, the 3, it does not have to go beyond 6. It can stay less than 6. And the 6 one has a limit of 9 because we're already sending a message to 9. So each of the messages going to 3, 6, and 9, because of these limits, it will remove all the redundant messages. We'll only look at a particular slice of the tree. So for example, the message coming in here, going to node 3, it has a limit of 6. the limit of 6 means that when this one sends its messages down to 4, 6, 7, 12, it will only send to the nodes that are less than 6. So it will send to 4, but it will not send to 6, 7, or 12. So there's a limit here. Because of this limit, this one will only send a message to 4. And it's not a problem because we have another message going to node 6. So because of the limit, we're basically slicing off part of the tree from each message going down. So basically, this gives us a spanning tree. If we go down 3, 6, 9, 3 will send to 4, 6 will send to 7, but not farther because the limit is 9. 9 will send to 10, 12, and 15. So in that way, we have 0 redundant messages. We're basically following the routing structure, and we're using a subset of the routing table. Of course, the broadcast will take n-1 messages. This is normal. We're sending to n nodes. So in any case, that could be too much. It still may be a costly service, broadcast, because each time you send a broadcast, you will be sending n-1 messages. Okay, so this is a question that still remains. We're not solving this issue, but broadcast remains a costly basic services. So we could actually prune or traverse the spanning tree in a different way if you want to reduce, to only look at a subset of that. So we actually made some results for the real DKS system. So we simulated the DKS, and we simulated a Gnutella broadcast and an efficient broadcast. So we have here on the bottom the number of nodes, and here the number of messages. Note the efficient broadcast, the number of messages is basically n-1. So 512 nodes will basically be 511 messages. Whereas the Gnutella-like broadcast is going to be doing much more redundancy. It's going to be, because it's covering the nodes, because many nodes will be in the routing table pointing to each other. There's a lot of overlap. So it's many more redundancy. And if you look at it in a different way, if you look at the message redundancy, that means how many of the messages are actually redundant or not needed. In the efficient algorithm, there's 0 redundancy. All the messages are needed. In the Gnutella-like algorithm, the redundancy goes up, and it goes up to more than 90% once we get to up to 1,024 nodes. So this broadcast algorithm shows that using the DHT structure, we can actually provide an optimal algorithm for best effort broadcast. So this is relevant if we want to start building services into peer-to-peer systems, for example, for group communication or complex queries. So concluding for this, so by using the distributed KA search framework for structured peer-to-peer systems with logarithmic performance, we're able to provide solutions to current systems. Notice that we gave this common framework. Notice that we can do group communication, broadcast, we can do complex queries, and we've shown how to maintain the structure using correction on use.